10 million people. This is the approximate population of Tajikistan, a landlocked nation positioned in the heart of Central Asia that currently ranks among the region's poorest territories. Despite possessing limited fossil fuel reserves and facing significant economic constraints, this small state is currently executing an infrastructure project that far exceeds its own domestic scale. Deep within a remote valley carved by the Vakhsh River, a monumental engineering feat is taking shape through the construction of the Rogun Dam. Why would a nation with such restricted resources choose to stake its entire economic future on a single hydraulic structure? While it seems like a disproportionate risk for a developing economy, the geographical reality of the region leaves little choice, as the massive potential of mountain meltwater remains their most viable path toward energy independence. Construction efforts are currently focused on reaching a staggering height of 335 meters. At this scale, the Rogun Dam is designed to become the tallest dam in human history, surpassing the height of any currently standing skyscraper or existing embankment on the planet. The project's total estimated cost is projected to reach approximately $8 billion, a figure that represents a massive portion of the national budget. One can notice how the immense concrete and rock-fill structure gradually rises against the steep canyon walls, where specialized machinery works ceaselessly to reinforce the foundation. It is visible how the sheer verticality of the design dwarfs the surrounding landscape, as heavy transport vehicles maneuver along narrow mountain paths to deliver materials. But this is just the beginning. The facility is engineered to generate 3,600 megawatts of electricity upon completion. This massive energy output is equivalent to the combined capacity of several nuclear power units operating simultaneously. The process of harnessing the Vakhsh River involves diverting immense volumes of water through complex tunnels before it reaches the primary turbines. Everything only gets more complicated when considering the logistical challenges of building such a colossal barrier in a seismically active high-altitude environment. Automated sensors and technical teams monitor the structural integrity of the site around the clock to ensure precision in every layer of the embankment. The camera glides along the massive spillways where the force of the water will eventually be managed by sophisticated hydraulic gates. It only looks obvious to build a dam where a river flows, but in reality, the pressure exerted by a reservoir of this depth requires calculations that push the boundaries of modern civil engineering. This ambition represents a total transformation of the national energy grid, moving the country toward a future powered entirely by renewable mountain resources. The massive structure continues to rise, marking a definitive shift in the industrial landscape of Central Asia. 1960 marks the decade when the conceptual foundation for the Rogun Dam was first established. Why was such a monumental engineering feat planned in the mid-20th century? While the project aligns with modern energy goals, it originated when Tajikistan functioned as a republic within the Soviet Union. During this era of the Cold War, Moscow implemented a strategic industrialization policy directed at its peripheral territories. Central Asia became a primary focus for these massive infrastructure developments designed to demonstrate technical superiority. The Vakhsh River emerged as the central geographic component of this ambitious plan. Engineers identified this major tributary of the Amu Darya system due to its unique hydrological characteristics. One can notice how the powerful water flow combines with high mountain terrain and an exceptionally sharp elevation drop. These physical conditions created one of the few locations globally where the construction of ultra-high dams was technically feasible. The process is only gaining momentum. In 1976, the Soviet Union formally initiated the Rogun project with a definitive strategic objective. The goal centered on creating a structure that would eclipse all previous hydropower achievements in both scale and function. This dam was intended to function as a singular mechanism for river control, massive electricity generation, and regional water regulation. It only looks obvious that such a plan would succeed, but in reality, geopolitical shifts intervened. Everything only gets more complicated. History deviated from the established engineering timeline as the 20th century progressed. Following the collapse of the Soviet Union in 1991, Tajikistan entered a period of internal instability and civil war. The national economy suffered a total breakdown, leaving the construction site in a state of sudden stasis. Rogun remained a partially completed skeleton of concrete and earth, abandoned to the elements in the mountain canyons. One can notice the silence that settled over the heavy machinery and excavated tunnels. It would take more than 20 years for the project to find the political and financial momentum necessary for its eventual revival. The site waited through decades of stagnation before the possibility of completion returned to the agenda. This transition marks the end of the project's initial historical phase. 1,099 feet is the final height the Rogun Dam will reach upon its completion. This elevation, equivalent to approximately 340 meters, will officially establish the structure as the tallest dam ever constructed on the planet. Why is such an immense scale necessary for this specific location? One might assume a smaller barrier would suffice for river regulation, but the project is designed to house 6 massive turbine units with a total installed capacity of 3,600 megawatts. This volume of energy is sufficient to double the entire current electricity output of Tajikistan, generating a massive surplus of power during the peak summer months. It only looks obvious that a dam of this height would be built from solid concrete. But in reality, Rogun is not a conventional concrete gravity dam. The engineering relies on a rock-filled design featuring a central clay core at its heart. Hundreds of millions of tons of rock and gravel form the primary body of the structure, with the equipment gradually compacting the material layer by layer to ensure maximum density. The camera glides along the massive rock-filled shoulders, which provide essential structural stability and energy absorption for the entire massif. Inside this shell, the clay core acts as a critical impermeable barrier, preventing any water from seeping through the embankment. But this is just the beginning. 13 cubic kilometers is the total capacity of the reservoir that will eventually form behind the finished barrier. This makes the site one of the largest reservoirs in the entire region, providing enough volume for seasonal flow regulation and stable power generation throughout the year. One can notice how the water level will eventually provide vital support for irrigation systems in various downstream areas. Everything only gets more complicated as the construction moves from theory to the riverbed. Why must the Vakhsh River be completely moved before the main dam body is laid? The process is only gaining momentum. To build such a massive structure, the foundation area must be kept perfectly dry at all times. For the Rogun project, this requirement dictated the drilling of massive diversion tunnels directly through the solid mountainside rock. Engineers designed 4 separate tunnels, each extending for a distance of more than 1 kilometer. One can notice the scale of the excavation, as diameters in these passages reach tens of meters. 2 of these tunnels were originally initiated during the Soviet era and required extensive rehabilitation and reinforcement to meet modern safety standards. The remaining 2 tunnels were successfully completed during the project restart phase. It is visible how these massive subterranean conduits allow the river to bypass the construction site entirely, ensuring the foundation remains accessible. The Vakhsh River flows through these man-made bypasses, allowing the dry site to transition to the next level of heavy construction. 100% of the weathered soil, loose rock, and unstable materials covering the valley floor had to be completely excavated before the Rogun Dam could begin to take shape. Why was such a massive volume of earth removed from the site down to the very bedrock? This deep cleaning ensures that the structure rests on a solid geological foundation rather than shifting ground. Excavators and heavy machinery stripped away the surface layers until they exposed the stable, unyielding rock mass. It only looks obvious to clear the path for construction, but in reality, the hidden integrity of the rock determines the safety of the entire project. The process is only gaining momentum. Engineers drill deep into the natural fractures of the exposed bedrock with mechanical precision to prepare for injection. High-pressure grout is then forced into these seams to seal off potential seepage paths and significantly increase the cohesion of the foundation. At first glance, the rock seems solid, but these injections are vital for controlling the movement of groundwater. One can notice how the drilling rigs maintain a steady pace across the valley floor. This is not the limit of the underground preparations. A foundation drainage system is installed simultaneously to manage uplift pressure beneath the dam for its entire service life. The equipment gradually integrates these pipes and channels into the base of the structure. This system acts as a permanent safeguard against the vertical forces of the water. Everything only gets more complicated as work moves toward the canyon walls. While the foundation is being treated, the rock slopes of the valley undergo a rigorous reinforcement process to prevent landslides. Workers install heavy steel mesh and drill long rock bolts deep into the vertical faces to lock the stone in place. One can notice how the shotcrete is sprayed in a continuous stream, coating the slopes in a protective layer of concrete. This reinforcement, combined with specialized drainage, ensures the slopes remain stable before the dam embankment begins. The core construction phase starts only after the foundation and slopes pass every safety requirement. Rock and gravel are extracted directly on site or hauled from nearby quarries by a fleet of heavy trucks. The material is laid down in thin, calculated layers that rarely exceed a few dozen centimeters in height. This incremental approach allows for maximum control over the density of the embankment. The process is only gaining momentum as the dam height increases. Bulldozers and graders level the stones before massive vibratory rollers begin the compaction phase. It is visible how the heavy rollers traverse the surface of each layer to eliminate air pockets and minimize future settlement. Each pass of the machine is recorded to ensure the dam remains stable for decades. At the center of the dam body, the core begins to form as a distinct element. One can notice how the transition zones protect this central part of the structure. The layers of stone rise steadily toward the crest of the valley. Thus, the foundation and lower embankments are prepared for the final stages of the assembly. 2018 and 2019 were the years when the first two turbine units officially initiated electricity generation. Why is the commencement of power production before full completion so critical? This transition marks the definitive shift from a massive construction site into a functioning industrial power plant. The electricity generated during this specific period serves a dual purpose, simultaneously supplying domestic demand and providing the necessary energy for the ongoing expansion of the facility. Monitoring systems track settlement, water pressure, and dam deformation with millisecond precision. Engineers inspect and test the operation of the discharge and control systems continuously to ensure every physical parameter remains within strict safety limits. One can notice how automated sensors record minute shifts in the structure. But this is just the beginning. Foundation works conclude while the spillway structures and vertical shafts are simultaneously carved deep into the rock mass. This involves vertical excavation and the systematic installation of reinforcement steel, followed by stage concrete placement. These components form safe water conveyance paths that manage hydraulic pressure during both the construction and operational phases. It only looks obvious to drill through stone, but in reality, these shafts must withstand immense internal force. Tunnel structures are assembled once the vertical shafts and horizontal tunnels have been fully excavated. Construction crews install heavy reinforcement and formwork before placing tunnel lining concrete in segmented sections. This process creates a load-bearing and waterproof barrier for the entire discharge route. It is visible how the metal reinforcement cages are locked into place before the fluid concrete fills the void. Everything only gets more complicated as the depth increases. Next, the tunnel invert and the floor of the discharge structures are finalized to establish a stable foundation for the entire system. Workers install drainage layers and reinforcement grids across the base. Concrete is then poured in specific segments while engineers maintain strict control over thickness, material strength, and surface smoothness. The equipment gradually levels the surface to prevent turbulence in the water flow. The process is only gaining momentum as the infrastructure integrates into a single hydraulic network. From here, the transformation moves to the next phase of processing as the remaining units are prepared for synchronization. Thus, the dam reaches a state of operational readiness, allowing the power plant to fulfill its role in the regional energy grid. 2029 is the year when the massive dam body is projected to reach its final design height, according to current engineering schedules. Why is the timeline for filling the resulting reservoir extended over such a vast duration? While the structure itself will stand complete, the process of reservoir impoundment will be executed with extreme technical caution over a period spanning several additional years. It is visible how the water level will rise gradually until 2036, the specific point when the Rogun Reservoir reaches its maximum operational elevation. At first glance, this seems like a simple delay, But in reality, it ensures the dam can finally fulfill its dual roles of river regulation and large-scale power generation without destabilizing the regional hydrologic balance. But this is just the beginning. $6.3 billion is the estimated total cost required to bring this industrial giant to life. For the nation of Tajikistan, the Rogun Dam functions as much more than a hydraulic engineering project. It represents a financial gamble on a national scale. The camera glides along the massive construction site, where every cubic meter of concrete represents a significant portion of the country's economic output. One can notice that this total expenditure is equivalent to nearly 50% of the entire national gross domestic product. For a small economy characterized by limited domestic revenue and a heavy structural reliance on external remittances, such a commitment creates an unprecedented level of financial strain. Everything only gets more complicated when considering the history of the site. Rogun suffered through decades of severe funding shortages that halted progress and left equipment dormant. International donors continue to maintain a cautious stance toward the development. This hesitation stems not only from the immense physical scale and inherent technical complexity of the dam, but also from the intricate political risks that permeate the project. It only looks obvious to build for energy needs, but in reality, the regional implications are far-reaching. The process is only gaining momentum as geopolitical factors enter the equation. Downstream nations, with Uzbekistan being the primary example, remain at the core of these international concerns. Their expansive agricultural sectors depend almost entirely on the consistent flow of water from the Amu Darya river system. The prospect of an upstream neighbor controlling a massive reservoir of this magnitude raised immediate and long-term water security fears throughout the Central Asian region. Because of these tensions, the World Bank established strict prerequisites for its involvement. The organization demanded a series of independent feasibility studies and exhaustive regional impact assessments before providing any support. The equipment gradually continues its work as these diplomatic and technical evaluations conclude, moving the project toward its final operational state. 185 meters is the height of the concrete wall that defines the energy landscape of a modern superpower. While smaller nations in Central Asia view projects like Rogun as a gamble for survival, this structure acts as a demonstration of how a single dam can reorganize the economic and energetic order of a continent. The Three Gorges Dam has effectively become the backbone of an interconnected hydropower ecosystem spanning the entire Yangtze Valley. Why was such a massive scale necessary for a single river project? It only looks obvious to describe it as a power plant, but in reality, the structure creates a reservoir so vast that it has physically reshaped the geography of the Three Gorges region. One can notice how the equipment gradually manages the flow of water for a territory inhabited by more than 400 million people. At its peak capacity, the megadam can eliminate up to 100 million tons of carbon emissions annually. But this is just the beginning. The most profound impact of the structure remains its quietest function in the form of flood control. The Yangtze Basin historically suffered from devastating floods that claimed thousands of lives. In 1931, the rising waters killed more than 145,000 people directly. Years later, in 1954, the death toll surpassed 30,000. By 1998, the raging river swept away thousands of villages, causing over 3,000 deaths and tens of billions of dollars in economic losses. It seems simple to view these as mere statistics. However, these figures represent the reason China committed to taming one of the most unpredictable and destructive rivers in Asia. The process is only gaining momentum. To secure the region, engineers had to build a water shield of unprecedented strength. The camera glides along the massive base where the construction journey began in 1994. Engineers first focused on preparing a foundation capable of supporting a concrete structure taller than a 60-story building. One can notice how the massive manipulators and drills worked to stabilize the bedrock. Everything only gets more complicated as the weight of the concrete begins to press down on the earth. This initial phase established the physical footprint required for the transformation of the Yangtze. The material is ready to move to the next processing phase without haste. 2,335 meters in length, 181 meters in height, and nearly 115 meters of thickness at its massive base. This monumental barrier must withstand the relentless pressure of billions of tons of water pushing against its surface every single day. Why was it necessary to excavate so deep into the earth for this structure? It would seem that the natural valley floor provides enough stability, but in reality, the weight of the reservoir would collapse any foundation not anchored to the ancient crust of the planet. Only solid, unfractured bedrock could serve as the support for a megadam of this unprecedented scale. Tens of thousands of workers removed an enormous volume of earth and rock to reach the required depth. The camera glides along the vertical walls of the deep foundation pits that were carved out until they reached granite layers hundreds of millions of years old. Each pit functioned like a detailed geological cross-section, exposing the primary backbone of the Three Gorges Valley. The equipment gradually cleared away the loose debris to reveal the crystalline stone beneath. But this is just the beginning. A massive network of grout holes, stretching for thousands of meters, was drilled into the exposed granite with jewelry-like precision. One can notice how hydraulic rigs penetrate the stone to create a dense grid of deep vertical channels. Engineers then injected these thousands of holes with a specialized cement slurry under high pressure. This process bonded the entire rock foundation into a single unified block, sealing even the tiniest microscopic cracks within the stone. Everything only gets more complicated as the depth increases, but the goal is to ensure that water cannot seep under the structure. The molten-like cement mixture fills every void, transforming the natural granite into an impenetrable subterranean wall. The bedrock and the artificial seals now function as one cohesive unit. The foundation reaches its final state of readiness to support the weight of the massive concrete monolith. Thus, the geological preparation concludes, allowing the construction to proceed to the next phase of reinforcement.